Hello and welcome back to day 6 of my Advent of Code 2024 solutions in ARM assembly for the Game Boy Advance. We are up to day 6 of 10. Let's get into it. Today is actually a very interesting day. We've been teleported I guess, back in time to 1518, and we are in a manufacturing lab. There is a guard patrolling the lab, and we want to search the lab without being caught by the guard. So we want to work out where the guard will be ahead of time so we can search safely, right? So we have our guard, he's in over here. We've got these hash marks are obstacles, right? Obstructions. And there's a bounds area, right? Out of bounds area. So he follows a very strict patrol protocol. If there is something directly in front of you, turn right 90 degrees. Otherwise, take a step forward. Right? So just walk forward until there's an obstacle, then turn right. Alright, so the first one, he just, where are we? Just goes straight up until he hits this obstacle and turns right. Until he hits that obstacle, then goes down. And he hits that obstacle down there. Then he turn right again. Until he hits that obstacle, and then that obstacle. And then that obstacle, and then that obstacle, and then this obstacle, and then that obstacle, and that obstacle. And then he would go, finally, you'd exit the bounds of the area, right? The guard eventually leaves the mapped area. So by predicting his route, we can determine specific positions on his patrol path, including the guard's starting position. All the positions get marked with an X, and the guard will visit 41 distinct positions on the map before exiting the area. And that's our part 1. Right. For part 2, we want to work out, say we're pretty sure that adding a single new obstruction won't cause a time paradox. They'd like to place a new obstruction in a way that the guard will get stuck in a loop, making the rest of the lab safe to search. In this example, there are 6 positions. You can stick an obstruction and the guard will get stuck in a loop, for example, and you can't stick one at the very beginning position. So you can stick one there, and when the guard comes back to a starting position, he'll hit the obstruction and continue on a loop. Another place, you can stick one there, right? It'll go up and around. You go up, then go across, go down, then go across. Go up, go across, go down, and you hit that there. And now he's stuck in this loop. It'll be a loop like this. Right, you're just going in this loop. Right. So, for part 2, we want to find how many positions, how many places we can put an obstruction that will get the guard stuck in a loop. Right? And that's the real hard part of this one, right? Of this day, because the naive way is just to try every location on the map. Just put an obstruction. Say there's an obstruction there, every empty space, and then run the system and see what happens. Right? Does he get stuck somewhere, or does he exit the map? If he exits the map, it doesn't work, and you have to have some kind of loop detection, right? If you don't have a loop detection, it will just run if he gets stuck in a loop, it will run infinitely, right? So that's the trick. You've got to, that's the naive way, sort of thing. Anywhere and loop detection. But there is a better way, and we'll go over the better way in my code. Let's have a look what I did this time. So what we've got here, we've got some places in memory. result, grid width, I'm storing the grid width. I'm trying to remember if I really need the grid width this time. It doesn't really matter. We'll find out soon. Grid mem. So I've got this grid mem here. It starts at 160 into the internal RAM, and I've got a very large area up to 17,408 available for that grid to fit into. So what I'm going to do is I'm going to copy the input grid into memory. Usually the previous days when I've had a grid problem, I've just used the grid, I've navigated the grid with a cursor in the ROM without copying it out to memory or anything. This time I'm actually copying out to memory. I think it just makes it a little bit easier in this one, right? Makes it just a little bit easier. And then I've got test path. And that's going to come in for part 2. So solved A, right? We set up our read pointer and the end of our input. 10 we stick to 0. We subtract 1. Right, I subtract 1 from the wait a second. Right, I subtract, this is the length of my input, right? I subtract the start of the input from the end of the input, and that gives me my length. This is an R1, and then I've got grid thing here, grid mem, my memory location of grid mem. So I load a byte from the input and I store it into grid mem, right? First byte, and then I add 1 and I compare to R10. No, I compare to R1. R10 to R1 to see if we are at the end of the input or not. And then we branch back. So it's just our copy. We're just copying it out of into memory, right? Then I load this up again. R8 is grid mem. So now instead of using input, right, I'm using grid mem. Then I move that to R7 as well, and I add the length of the input to it. I think I add add that to it. I should be using right, and that goes into R9, which is the length of well, it's the end address of the input in memory. Length address of the grid in memory, right? Basically the same thing as I'm doing up here, as I have up here. So we've got that. Then I make 10 0, and now I'm getting the width, right? I go through that input, look for an OA, which is and saying, of course, I need the grid length to still navigate through the grid. Yeah, find the first OA, add 1 to it, and store that in to the grid width location, right? And then I have to find the start. So we keep going until we find 5E, which is that that up sign caret. I can't remember what we call it. Caret? I think it might be caret actually. Right. And we get its location. Right. And then I move R8 to that position. So I think I can always check grid mem anyway to see if I go out. It looks like I'm using R8 still to navigate around the grid, but that's all right. I put R3, this value here, which I believe is a capital X. I'm going to use capital X, and I store it into the grid in memory, grid mem, into the location of the start menu. So I'm changing the location that I started at to an X. and that shows that I've already been there, sort of thing, right? And now, so we're ready to start moving. We'll start the guard moving through the grid, right? So here's R6 is going to define what way I'm moving, right? North, west, south, east. That's my pattern. I load into R1 the value of R5, which was the grid width, right? And then we loop through our grids, right? So we compare R6. What is R6 right now? If it's a 0, then we subtract the where are we? Where are we? R8, right. R1, the grid width here, right? If it's so I'm always putting it into R10. That's like my temporary location. I'm always the attempted move, right? The attempted move goes into R10. R8 is my present location, right? So we compare R6. If it's a 0, then we subtract the grid width and put that into R10. So that would be moving upwards in the grid. If it's 1, then we add 1 to it, which would be moving to the right. If it's 2, then we add the grid width, and then we compare that, right? And we add the grid width, which is moving down in the grid, or south. And if it's a 3, then we subtract 1, which is moving left or east in the things. And then we'd branch to gold eval, which is where we're looking for a potential loop, right? So we'll check that a little bit later. We'll check that after we go through this rest of this, I think. So what we do, the silver part really, we load the value that's in the grid at that location, R10, where we're trying to move to. We do a balance check, right? For out of balance, we've finished. Remember we've done balance check before. The result comes back on R2. Let's have a look at the balance check, right? Remember, we don't back up the registers as we go into the balance check. That's fine. We set R2 to 0. We see if R0, which is the location we are on the grid, is an OA, which is the left or right bounds, effectively. If it is, then R2 becomes 1, and we return. We check if it's less than R7, which was our beginning of the grid, right? And if it is, then if it's less than the beginning address of the grid, then we've gone out the top bounds, and so we put that into 1 into R2, and then we check the lower bound, the same thing, R9. We check if we're greater than or equal to R9, and if it is, then we've left the bottom bounds, right? Otherwise, we just return. R2 would return as 0 if it got through all of that. Okay, I'm looking at R7. I'm like wondering why is it R7 in there. My grid mem goes into there as R7. Yeah, no, that's okay. We could have used it somewhere else, I guess. Like, I mean, we could have used like oh no, not there. Maybe R5. What's R5? R5 is grid width. No, like I said, is R7 is the place to use it, really. Okay, that's fine. Everything's fine. Situation normal. So come back from the balance check. We check if R1 is R2 is 1. If it is 1, we are finished. We've exited the bounds. Silver's complete. Gold would also be complete because we can't place a an obstruction out of bounds. And would branch to finish day, right? Finish day. We just load the result of res1. We add another 1 to it and we put it back into the result. That's a little bit interesting. I'm wondering if that's, yeah, I see a potential bug here, I think. Or I could get it off by 1. So I'm down here. I have the BL enable interrupt. I should check this. That 1 might not even be necessary, and it might be a lack of the enable interrupt that's preventing it from outputting. That should be there as well. That could be fun. I mean, if it is a bug, then I should just get rid of all of this. Anyway, who cares? We'll deal with that in a little bit. Anyway, so that's if we've reached the exit, we've exited the bounds. Otherwise, we compare R0 to ASCII 23, which is a hash symbol. If it is equal to that, then we are doing a turn. We revert our position, so we're not on top of it anymore. Would branch BL to add path, and then would branch to loop grid. Right, branch to loop grid is up here somewhere. Yep, right. This thing here again. Add path, branch EQ would go to, we do this anyway, right? Regardless of this compare, we do the move and these two branches regardless. We only do the do turn if it's thing. Right? Oh no, we're not reverting. Right? We're updating R8. So if we don't do the turn, we update R8 to be the value from R10. Yeah. So if it is a obstruction, we go to this do turn. We add 1 to R6, which you know, so if it was 0 it become 1, 1 becomes 2, 2 becomes 3, then we compare it with 4. If it's 4, then we change it to 0, and then we branch to the loop grid. Yeah, that's fine. All right. So it's only if we don't turn that we update R8. We update R8 to equal R10, the contents of R10, and we do branch to add path, and we do loop grid, right? So there's one more thing there, add path. So we're going to we load in the value from R8, we compare it to 5.8, which is a capital X. If it is a capital X, then we exit this add path. If it isn't, then we take this capital X and we store it into the grid in memory, right? So we want to mark all the positions we've been with a capital X. And I mean, this isn't actually important for part 1. This isn't important for part 1. This is important for part 2. Okay? For part 1, I mean, we could just add. Actually, no, this is kind of important for our part 1. Because we have to do all the unique locations. Right. Okay, so yeah, it is important for part 1. Sorry, it is important for part 1 as well. There are other ways you could do it for part 1. You could just keep a track of all the memory locations, all the register values I'd been in. Like, just keep that on a list. But I think this is, well, this is better really. Right? Instead of having to search through a list of memory locations to say, hey, have I been here or not? I'm just checking the location I'm at. Right, I'm just checking the memory location I'm at. If it's an X, then I've been there already. I don't have to like search a list or anything like that. It's just, yeah. Right, so only if it was not an X do I store the X into that location, and then I update the result to add +1 to it, and then I enable the interrupt, which will update the value on screen. Right, this is where I've updated the my rendering so that the interrupt disables itself, and I enable the interrupt, the vblank interrupt, whenever I update the result values. So it spends a lot more time with the CPU actually doing the solving the problem, and not updating the result when there's been no changes. Right. It's more important with this one because there's quite a lot of computation that has to be done before you might actually get a result change, like a value change on the result. Alright, so that's get path done. Like with this is finishing silver, that's great. But every time I move, I'm going to branch to this gold eval. Right, every time I move, I'm going to branch to this gold eval. So what am I going to do in gold eval? So where are we here? Right, we enter into gold eval. I'm going to put R5. I'm going to load R5 with 4 for some reason. We'll find out soon. We want to load the value that's in R10. We want to see what's there. If it's a brick, get out. Right? We don't, like, if there's already an obstruction there, we don't have to check if there's another obstruction there. Right? We don't. If there's already an obstruction there, we don't have to check if putting an obstruction there will create a loop. Right? That just exits. If it's out of bounds, abort. Right? Okay, so we move R8 into R11 and back that up, I believe. We move R10 into R8 and we do the bounds check. And that's just because I'm using R8, I think. No, wait. What am I doing in there? Move R10 into R8 and then branch into the bounds check. That seems a little bit odd, because I'm not even altering R8 at all in there. R10 gets used in the bounds check. Why am I backing that up for the bounds check? I shouldn't have to do that. R10 gets used. It may have been something earlier in the code, and then I changed it so that R10 is used in the bounds check, and then I just didn't revert it. That's always possible. Anyway, that's alright. I think I could remove all of that, really. I think I could just remove all of that and it'd probably be alright. Anyway, probably get rid of this here, and that there, and that there, and it'll probably be fine. Does it go in there with R10? Yeah, I think it should be fine. Then I also do this check in paths. I do this in path check. Here, right? I branch this in path check. And this in path check, if that returns a 1, then we break out. We exit gold test as well. So let's have a look at that in path check. Right. Very quick check in here. We move R14. This is our return address into R0. We load R2 with 0. Make sure it's 0. It should have been 0 already. That's alright. We load the byte from R10, and we compare that. Remember, R10 is the location we're trying to move to. Or actually, in this case, R10 is the location we're trying to put an obstruction. But anyway, we check if it's an X, and if it is an X, if it isn't an X, then we exit the path check. We just jump down to there, branch to there. If it is an X, you know what I should have just done here, I believe, just done this. I'm taking this thing here out. Then I could take this here out. Then I could take that out. Then I could take that out. Right, we go in here with R2. It's a 0. We load the byte that was in the location we're trying to go to. We compare it with R4 with a capital X. If it is a capital X, R2 becomes 1, and then we return. And then we return. If it's a 1, we exit gold test, right? So M11 is going to be our register 11 is going to become the location where we're trying to put an obstruction, right? We're going to test if an obstruction there causes a loop. So I should actually explain why we do this check clearly, right? If we are attempting to put an obstruction on a place that we have already visited, then we would have already hit that obstruction, right? If we're trying to put an obstruction in a position where the guard has already passed through, he would have already hit that obstruction anyway. You get me? I wonder if you get me. You probably get me. Let's have a look on here, right? So let's take not the simplest one, because if we use this one up here, we don't pass through any locations, right? When we put the obstruction down. Let's go for this one over here, right? It's going to go up, around, down, around, over here. The test obstruction is down here, right? So let's say we're coming back this way. We go upwards from here. Just don't go back here, and then we say, well, what happens if we put an obstruction in this location? Well, if there was an obstruction there, then from the beginning we would have gone up and hit it and gone to the right and exited the map, right? So it's an invalid attempt to put an obstruction there as we come across from the right. Right, so we can't put obstructions on any locations on the path that we have already trodden, and that's the point of this in path check. Okay, so that's that part. So we the place R10, which is where we are going to put. We're going to test if an obstruction will in that location will cause a loop. We move that into R11. Then we take our present location. That's, remember, our actual present location that we're moving from. We were trying to move from into R10. We take that location and we logically shift it left 2 positions. That location in memory. We logically shift it left 2 places, and we put that into R12. Then we add to R12 the value that's in R6, right? The value of either 0, 1, 2, or 3. Right. And so what I'm effectively doing here is I'm making a single value that contains the location in memory, the location on the grid that I'm at, plus the direction I'm facing. Okay, you get this? Because if I ever visit that location in the grid while facing the same direction, I'm in a loop. Okay? If I ever visit that again, that location again, facing the same direction, I'm in a loop. Because I'll carry along that path, I'll hit an object, and I'll turn the same direction as I did the last time. And I'll hit all the same obstacles I did last time. And I'll be in a loop. That's how you'll detect if you are in a loop. Right? So then I load test path, the location of test path, I add 1 to it, I store that, I multiply it by 4. I multiply it by 4. Remember, we loaded R5 with 4 up here. We're storing a word, 32 bits, so we need 4 bytes worth of space. Multiply it by 4. We store R12 into it, and then we store into R3 our count, our offset, the number of locations we have in test path. We add 1 to R6, we compare it with 4, and we roll it over to 0 if necessary. We move the value of R8 back into R10 because what was it? Why do I have to put R8 back into R10 here? Not quite sure why actually, but we do it anyway. Move the value of R8 back into R10. Yeah, I don't think I need to do that. It doesn't matter. Because what I'm going to do is that we're going to fall into this test loop, right? Where we load the grid width into R1, right? We compare R6, same deal as in the main loop, right? Oh, don't delete things, right? We comparing R6 to 1, 2, 3, 4. Oh, 0, 1, 2, 3. Sorry. And we either subtract the grid width from R8 and we put that into R10, so that's why I think this isn't not necessary. Or we add 1 to it, or we add the grid width to it, or we subtract the grid width from it. Right? We load the byte that's inside R0, and then we do the bounds check, which is using R10. Right? If we go out of bounds, then the obstruction that we used, or the obstruction that we're testing, doesn't put us into a loop, so we exit the gold test. We're out. Otherwise, we compare R0 with 23, which is a hash, right? If it's a hash, we do a gold turn. We also compare R10 with R11, right? R11 was where we are testing the obstruction, right? We stored into R11 up here. Delete again. Up here, the location of the potential obstruction. So if we find that location, we've hit it again, right? And we could be coming at it from a different direction, so we don't want to be testing, checking that actually no, I think I've got the test in there anyway, and do gold turn. That's fine. Anyway, we don't want to check that immediately, right? We don't want to go, oh, we've hit the same location that we were at last time. It must be a loop, right? We do the gold turn. We jump to gold turn. Otherwise, we update R8 with that location from R10 that we're trying to move to, and we go back to our test loop, and we keep doing our loop. Right. So if we've hit an obstruction, right, one of these ones here, we've hit some obstruction. We go into this gold turn. We'll branch into the test pass check. If that's comes back with a 1, we exit gold test. Branch to exit gold test. Interesting. No, I guess we're okay. Yep. We exit gold test. Right, we just branch back down to here, and we exit out. So this will be the way that we've discovered a loop, right? This will be the way that we've discovered a loop. It comes back R2 comes back as 1. We've discovered a loop, and we'll finish the gold test. We're out. Otherwise, we add 1 to R6, and we compare it with 4 to see if we have to wrap around, and we go back to test loop again, right? So, the last part, our test path check down here. So, what are we doing here, right? First, we're backing up R14. That's our return. Our return address for jumping back, branching back. We take our present location, R8. We logically shift it left 2. And we've put it into R12. We combine it with the position direction from R6, right? We add R6 to it, the same thing we did before. And then we load our test path. And we load how long test path is, our pointer. We compare it with 0. If it's like a 0 length, hey, we add it to the test path. I think that should never be true because we put 1 in there, but hey. Better safe than sorry, I guess. Right, we start putting a value in there, so that should never pass. That should never be true. And then we go into our loop test path. Right, so we multiply it by the value of R3 by 4. We load that index, the value from that index, into R1. We compare it with R12. If it's equal, it is a value that was in the test path that we've visited before, and we're branching to add gold, right? We've found a loop. So what I'm doing there, what you'll notice is that I'm only storing the locations where I impact, where I meet an obstruction. I'm not storing every location in the path that I'm testing, only when I hit obstructions, right? And that will keep the number of checks I'm doing much shorter, because I don't have to. I'm not checking like every position that I move to see if I'm on the loop. I just check when I hit an obstruction. Have I hit this obstruction from this direction before? Right? It makes the path a lot shorter, speeds up execution. If it's not the same as R1, right? If it's not the same that I checked in the loop, I subtract 1 from the index, go back up, branch back up over here, multiply it again, right? Try the next value. So loop through all the values that are in the test path. If I get to the end of that, there's no match. We add the value, right? So take the pointer again, we add 1 to it, we multiply it by 4, we store this encoded information, the position in the grid and the direction we're facing, we add that onto the test path, and we store it into the path, and we store the new pointer back into the path, right? New index, new length back into the list. Otherwise, we've found that we're in a loop. We add to gold, right? So we load the result of res2 right into R3. We add 1 to it because we found one more location that we could place an obstruction and would result in a loop. We store that. Then we move 1 into R2 to show that we've found a loop, that we should end the gold checks. Then we branch, enable the interrupt so that the result will update on the screen. And then we go through exit check path, we restore the return address, and then we return from this subroutine. And that's it. That is day 6. So first, let's have a look at this run, shall we? Let's have a look at this run. And then I'll rebuild it and see if those changes that I've made taking out these and adding in this enable interrupt if they make any changes. if I need to be adding this one onto the end up here. Actually, I can check that in memory. I'll check that in memory before we actually run it, before I actually compile it and see what happens. Alright, so let's get this running. This takes a little while, so we'll start it up. You know what? I'm going to bring up the memory already, and we'll run it with the memory visible, because it gets a little bit interesting in the memory, I think. So our internal work RAM looks very empty right now. Let's get started, shall we? There we go. Oh, you can see down here, this is all our grid in memory, right? If we look down here somewhere, we'll start seeing, oh, we've got values going up there. What have we got? Our obstructions. Oh, here's our X's. You can see our X's adding to the path for the silver that we're going along, right? Our results are going up there. And see, the grid is pretty long in memory, really. Our path is going nuts over here. Right. If I had this much wider, it'd be easier to see. The grid is huge in memory. Look at it. And oh, and here we are with part 2. Right. These are all the test paths. I don't clear out this list every time. I just clear out the value up here, the length of the test path list, and so it will just write over as much as it needs to. So you see it there, testing, counting up the golds. So that gets fairly long as well. Like you can see here, I'm over halfway down the internal memory, which is 24 kilobytes, I think. So I'm using a good chunk of the internal memory. It's going. Right. Testing all the paths it can. This here. Can I get this wider and actually see it on? Oh, and we can get it a little bit wider on there. Although I'm covering up there now. That's alright. We'll leave it counting, shall we? Back down, and I think it's done. Is that done? That is done. Let's verify this, shall we? So if I look in the memory, it does look like the result is correct. We have 4973 there and 1482 there. That looks right. If we look on our, let's show up our browser. I can see there as well, right? Where are we? This here. Let's get rid of this for a second. We can see 4973. Yeah, that's right. And down here somewhere. There we are. Can't see if we can see that on screen or not. I've gone too far. Let's go up a little bit. There we are. And 1482. Alright. There's our result. Alright, so let's recompile this. Right. Let's recompile this. Let's see if I broke it. Or let's see if it still works. It's always fun. It's like, wait a second, what is it? Wait a second, why am I doing that? And then, you know, change it and then see if it still works or not. It's always fun. Is it just me or is gold going up too slowly? I don't know. You never know. But just in general, at the beginning, there aren't going to be so many loops, if I recall correctly. They already start appearing later on. But yeah, I think this takes about 4 minutes to run, which is a little bit on the high side. It's not the longest solution I have. It's definitely not the longest solution in code that I have. but it's certainly not the longest running solution I made in this Advent of Code. I think that was actually tomorrow's one, so that's something to look forward to. I'll spare you watching that one run in real time. Well, I improved that solution after the fact. I'll spare you watching the original run in real time. That's what I should say. Alright, it's going up fairly quickly now. It looks like the gold is catching up and might get there. Let's see if it's broken or not, because it should be like 4, 3 something now. It looks like it's getting pretty good. $1,482. The gold is still fine. What was the silver again? 4,973. Silver's still fine. Okay, yeah. So those changes, they were fine. They didn't break it. I didn't break it. Thank goodness. Thank goodness. All right. So that was day 6. I think that was a very fun day. That was one of the highlights of this Advent code. At least for the Game Boy Advance. All right. Tomorrow is probably even more fun. So it could take a while to explain, but we'll power through it. All right. So I hope to see you again next time. Cheers.